This is the first of a three-part video dealing with the topics of expected value, population distribution, and the data generating process. So we need to start off by clarifying the meaning of population, which we'll actually prefer to think of in terms of a data generating process. So how is a sample different from a population? Well, here's a first example, which is the way we often think about it. If you survey 500 employees in your company, well, that's a sample. The full population consists of all employees. That's the population that you've sampled from. This little example is useful in many cases, but definitely not in all. So for example, when we think about the roll of a die, if I roll a die 60 times and make a histogram of my 60 rolls, it might look something like this. Here I've recorded how many times I rolled: 1, 2, 3, 4, 5, 6. Now I want to think about this as a randomly generated sample. But what's the population that I've sampled from? In some sense, it's the population of all possible rolls. And here's what that population looks like. The possible outcomes are 1, 2, 3, 4, 5, 6. But a feature of this population is that each of those outcomes is equally likely. So this is the population distribution. It's described by having equally likely probabilities if we're dealing with a perfect die. Now, it's a little bit strange to think about this as a population. It's better to think about it as the data generating process. This is a description of what happens every time you roll a die. So each time I roll a die, I'm drawing a random variable x from this distribution, and then my histogram just records the outcomes of repeated draws from that distribution. What's the relationship between these two? Well, as we just described, this underlying distribution generates the data, and then if we roll enough times, we imagine that eventually this histogram of our actual rolls is going to look more and more like our underlying population distribution, in the sense that each of these outcomes should occur roughly the same number of times if we have a perfect die. In other words, if this is an accurate description of the data generating process. Let's look at a second example, stock index returns. Here's a histogram of daily returns from the stock market. This is our data. We can think of it as being sampled from some underlying population, but what's the underlying population? What is the population of all possible stock returns? Well, again, it's better to think in terms of a model of the data generating process. And so our model might be that daily stock returns come from some theoretical distribution that looks like this. Every day, the market draws a random variable x from this distribution, and that gives us a new observation in the data. Over enough time, if we keep observing enough samples and making a histogram of the samples, we might imagine that this histogram of the samples is going to look more and more like this population, if in fact this is an accurate description of the population. For our last example, let's look at the iOrigins experiment. So Salamina is presented with 25 cards, each of which has 3 images, and she's asked to pick her favorite, and the experiment is to see how many she guesses correctly. Well, a person guessing just at random would have a 1/3 chance of picking the correct image from each card, because there are 3 images, or at least that's what our assumption is going to be. So across 25 cards, the person might score as few as 0 correct, or might get a perfect score and get all 25 correct. And this picture here illustrates the probabilities that somebody guessing at random would get 0, 1 correct, 2 correct, 3 correct, and so on. And now we're not going to worry about exactly where these probabilities come from. They're something called a binomial distribution. But what matters for our discussion is that we have a model that describes the probabilities of getting 8 correct, 9 correct, and so on if you're guessing at random and have a 1/3 chance of picking the correct image each time. Now, every time somebody does this experiment with 25 cards, the score that they get is like one draw of a random variable x from this distribution. That's the way we want to think of the underlying population for random guessers. Looks like this distribution. Every time we run the experiment, we're getting one draw. How did Salamina do relative to the experiment, given that relative to the population, given that she got 11 correct? So we might ask, what is the probability that someone guessing at random would do as well as Salamina or better? Equivalently, we might say, what proportion of the population is 11 or better, scores 11 or better? Okay, so we're asking for the probability that a randomly drawn x will be greater than or equal to 11. So we just need to add up the bars. These give us the individual probabilities, right? And it turns out that that's 17.8%. So it's actually not so unusual for somebody just guessing at random to do as well as Salamina or better. Nevertheless, it does seem that Salamina did at least above average compared to a random guesser. So in the next video, we need to introduce the concept of average or expected value when we're dealing with a probability distribution.